afternoon, everyone. My name is Luka Svet, and today I'm going to give you an overview of a project that deals with the dynamics of bacterial populations in various environmental conditions, which particularly focus on such dynamics under the administration of antimicrobials, which I, together with my colleagues, have been working on for quite some time and also intend to develop it further in the future. Now, to understand the project a bit better and to have an idea of the reasons why we are doing what we are doing, let's first have a look at the historical background and current problems surrounding the use of antimicrobials. Now, it's widely accepted that the discovery of antimicrobial compounds represents one of the most important findings of the previous century. However, the overuse of antimicrobials has contributed to an accelerated resistance development, leading to the evolution of multi-resistant bacteria, which are also, maybe you've heard, commonly known as superbugs. Now, this public health crisis is exacerbated by the lack of investment in the development of new antimicrobials by pharmaceutical companies and has led to shortage of effective antimicrobials to treat the infections, and according to some reviews, at least 700,000 deaths per year are associated with this resistance to antimicrobials, and unless action is taken, up to around 10 million deaths will be caused annually by year 2050. So the mechanisms behind the actual development of antimicrobial resistance have been previously considerably covered in the literature over the past few decades. However, most of this literature focuses on the evolution of AMR in microbes grown in an artificial, in laboratory settings, specifically, for example, in liquid culture that are shaken for a longer period of time and then subjected to various concentrations of antibiotics. But such conditions entice a completely different phenotype from the microorganisms as we usually expect from them to have in nature. So we expect them in nature to be usually in a tightly packed, heterogeneous and organized communities surrounded by some kind of slime layer, which are usually called biofilms. Now, these biofilms are often associated with considerable problems in medicine and also industry alike. And for these communities, proper solutions are still need to be found. Now, a particular peculiarity of biofilms within which the microorganisms reside, and for which also we are researching them, is that they experience an increased tolerance when subjected to antimicrobial treatment, and furthermore, it has also been observed that biofilm environment leads to rapid genetic diversification and adaptation to either anthropogenic or environmental challenge. But surprisingly, despite this, the evolution and development of antimicrobial resistance with respect to biofilm mode of life has been seldomly studied, and little literature exists about it. So in this study, we therefore aim to broaden the knowledge and available tools in the field of antimicrobial resistance, with particular focus on biofilm communities by employing mathematical modeling and specialized software to follow the evolution and spread of resistance in such populations. You might ask yourself, why is this even needed? I mean, why not just perform classical laboratory experiment and observe how bacteria evolve over time? I mean, this is indeed possible, but it has several drawbacks. I mean, the main advantages of using mathematical modeling to probe into the aforementioned mechanisms is that it enables us to transform biological processes into some kind of structured framework of adaptable accuracy based on our requirements. It also allows us to perform experiments in a tightly controlled environment with a higher degree of oversight over the conditions and less interference from undesirable extraneous variables, such is the case for the regular laboratory experiment. And also, basically, the duly constructed model permits the reproduction of empirical findings in the same way as would be the case for a classical laboratory experiment if it would be repeated using more, let's say, traditional wet lab techniques. So basically, we are able, if the model is good enough, predict pretty much the same outcome. Now, sadly, with the advancement of the information technology, more and more sophisticated models have been already developed, but they are commonly not entirely modifiable with regards to parameters. They are inconvenient with the steep learning curve for people with no programming background, and also what was important for us is that there was little attention paid to the dynamics of populations within biofilms and how the resistance evolves in such cases. So to address this issue, we created a computer software which is actually based but significantly modified on an article from 2019 by David Sapinto Nogueira. The program is able to model the population dynamics of bacterial, planktonic, and also biofilm cells within the same microbial community under the influence of antimicrobial treatment or without. And we are particularly focusing, as it says also here, so on the emergence and spread of antibiotic resistance. The application, it's easily configurable. There is little technical knowledge required to use it. You can manipulate almost every parameter, and at the same time, to a certain degree, let's say, it enables verification and prediction of certain hypotheses. Verification of scientific hypotheses and predictions. So on the following few slides, you'll see several examples of the usage of the aforementioned program and the model, and of course, results that it produces. I must say that the software and the model itself are still work in progress, so their functionality is not yet as good as we would like to, but this will nevertheless be expanded in the near future. For example, our goal is to maybe not replace, but at least be able to a certain degree, evaluate our wet lab experiments, so the evolution experiments, to see if the model predictions actually give the same results as what we see in the lab experiments. But anyway, in the example number 1, you can see the course, or this example represents the course of bacterial infection within a human host that is allowed to run its natural course without any medical interference, so without means of antibiotics, and it's this simulation was run under the assumption of a functioning immune system. Under such conditions, all bacterial populations initially proceed to grow exponentially and almost unrestrained, while the proliferation of the immune system cells lags behind. Now, this remains the case until the density of immune cells reaches such a value that they start noticeably affecting the survival of all 4 bacterial populations, which happens approximately 6 days simulation-wise since the start of the infection. And then the whole infection is completely resolved by the 9th day of the infection, of the simulation. In the next two examples, we wanted to emulate the response of bacteria to antibiotic treatment of various lengths and commencement times. The rationale of examining this effect lies in the fact that a too short administration regime might lead to a higher rate of treatment failures as compared to common course length, as well to potentiate the problem of antimicrobial resistance evolution due to intermediate levels of antibiotics in tissues. What I mean by that is that the levels of antibiotic might not be high enough to completely eradicate the pathogen, or the antibiotic might be administered for too long, and it might lead to high continuous selective pressure on sensitive bacteria and contribute to an acceleration of the emergence of resistance. So specifically, those two examples demonstrate a scenario where an antibiotic treatment regime is terminated prematurely. So in the right figure, the antibiotic treatment lasted only for 3 days, as compared to the left figure, where the treatment lasted for to a commonly prescribed full course of 7 days. Now, in the left figure, a sharp drop in the population size of antibiotic sensitive, both biofilm and planktonic bacteria, is observed as soon as the antibiotic administration commences, and they are driven extinct before the end of the 7th day. Now, antibiotic resistant cells, however, persist and are only extinguished by the immune cells, by the immune system long after the therapy has been completed. In the right figure, initially, you see the same dynamics as on the left one. However, due to early interruption of the therapy, only 3 days since the beginning of the administration, the antibiotic is unable to completely eliminate the sensitive bacteria. This, in turn, results into a much higher total pathogen load by a factor of approximately 82, and also in a much higher activation of the, or let's say higher activation of the immune system. It's by a factor of 3. Now on this slide, here are actually the last 2 exemplary scenarios. We didn't focus that much on the progress of an infection in a human host, but tried to evaluate the possible effect of antibiotic treatment on bacterial populations in an environment devoid of immune system. So, for example, in an artificial laboratory environment or industrial environment. The results on figure 4, the left figure, this is the left figure, portray a scenario where the antibiotic treatment is applied continuously since the beginning of the experiment, and thus, significant selective pressure is exerted on populations of sensitive bacteria. This in turn influences the total composition of the community, with resistant bacteria quickly becoming the only surviving inhabitants of such a system. So these results on the left figure illustrate a potential problem where an insufficient, also illustrate where an insufficient amount of antibiotics fails to completely eliminate the resistant populations of bacteria, and in turn lead to development of resistance. On the right figure, this is a figure of a simulation where the antibiotic treatment commences at the end of the 4th day since the start of the bacterial growth and lasts for a little more than 6 days. All populations of bacteria experience a steep drop initially, while sensitive bacteria are completely eliminated before the end of the treatment, as well as the resistant planktonic bacteria, but resistant biofilm bacteria are, however, not completely eradicated due to insufficient time of antibiotic administration. In real-life conditions, such a scenario could possibly lead to a situation where only resistant bacteria remain, and such resistant biofilm bacteria are usually very hard to completely eradicate, and they might additionally contribute to the problem of antimicrobial resistance, evolutions of the problem that I've been talking about all this time. In conclusion, both of these scenarios, the antibiotic treatment fails either due to inadequate concentration or due to insufficient time of application. Okay, we have arrived almost at the end, and thus I hope I was able to illustrate the results and the goals of the here presented project. We evaluated several different computer simulations to monitor the dynamics of bacterial communities by varying a diverse range of parameters that correspond to various environmental conditions. So the software provides us with a way to make the study of the emergence and spread of antimicrobial resistance more feasible, while at the same time it also in a way demonstrates its potential predictive capabilities. The software and the model are, though, not without their drawbacks. Adjusting the model's parameters in a way that they would correspond to real-life conditions might be a bit tricky, and as such the simulations and the results need to be carefully evaluated. Furthermore, I would also like to say that individual-based models might provide a better approximation of population dynamics particularly in biofilm. So with this in mind, we plan to further improve our software and our model, and to also perform some experimental validation to see if it's actually useful in a way or not. So that would be all from my side, and thank you for the attention.
Thank you very much. Again, very nice presentation. A lot of applause, I see. Very nice. Yeah, so again, if you have questions, don't hesitate. Put them in the question tab on the right of your screen. Meanwhile, I maybe have a question just on your conclusion. You say adjusting the parameters of the model to fit the real data is difficult. Could you maybe comment a bit on that?
Yeah, basically, I mean, we have a model, but it's not validated on any of the experiments. So we see certain dynamics in the results, but we do not know if this really happens. So this is a bit of a problem. So yeah, we have a model and the results, but they maybe are just like fantasy.
Okay. But so you have real data. Do you think? Well, yeah, I get it. It's easy to say, but very hard to implement. But do you think this, like, there is a component of, let's say, the reality that you miss in your model, or do you think it's because you need more data to better fit the parameters?
I think more the first part. So there are components in the model. We are not yet sure which are the most important, but for the biofilms, there are several different things, let's say attachment rate, then dispersion, and many different things that might influence how the dynamics will evolve. And we are not yet sure which should be taken more into account and which maybe we can just disregard.
Okay, understand. And maybe I think you discussed it you introduced it at the beginning. But so in your last figure, you clearly show there is a difference when you have biofilm or if you have how this is planktonic.
So those just freely swimming bacteria.
Yeah, freely. I mean, do you have an idea of mechanistic effect of why this is so?
In a sense, why they are more tolerant, or
more tolerant.
I mean, this is also, let's say, more hypothetical. I mean, I will say it like that. It's not been completely proven. There are studies that show different things. In some cases, they are more tolerant, in some cases not, and there are also different explanations. But one of the explanations is simply that because they are surrounded by, let's say, a protective layer that they produce, they are less influenced by the antibiotic that comes from the outside. So the concentration of the antibiotic that reaches them in the middle of that biofilm is lower than for planktonic cells that are just freely swimming around. And there are also several other things, but I think this is one that is mostly mentioned in studies of that.
Okay, cool, thank you. And then Rafael is asking, have you considered doing a deeper parameter sensitivity analysis then?
Well, yes. At the moment, this I think would be the next reasonable step. To actually to research what is actually important, and then to compare the predictions that the models with the parameters that we give it make, and if this corresponds to the actual results we see during the wet lab experiments.